Hello, everyone, and good day, good morning, good day, good afternoon, good evening, or good night, wherever you are in the world, and welcome again to Freaky Physics. Yes, we are gonna have a lesson today, same lesson from last Thursday. That was 2 days ago. We have Gita today, and we are gonna continue with those problems we were doing last time. Okay. Uh, yeah, I'm feeling a bit better today. And with that, I think I should be able to get in, no problem with what we need to do today. Right, so I'm gonna join the class now. Let's go. It's already you're in. Okay, let's join the lesson right now. Hello, Gita. Good
Hello.
day. How are you today?
I'm good. How are you?
Doing better. I'm definitely feeling better compared to last time. Okay,
That's good.
great. Well, okay. So you sent me a few problems from last time again. We still didn't finish a few problems, right? Specifically, we didn't quite finish the question about the heat engine and then about the liquid boiling, right? Okay.
And entropy.
And yeah, the one about entropy. All right. So let's go back to this question. Last time, we were trying to figure out what the answer was, right? But I was really at the back of my mind, there is missing information here. You said the answer was 16%, right?
Yeah.
Okay. The reason why I think there's missing information here is when I check, no matter what I do, I couldn't get to any of these numbers. Okay, because the idea here is we need the efficiency of X to know what the efficiency of Y is. You get
Okay.
all right. So I really feel like there's something missing in this question. Otherwise, if we knew what the values were for and at least two of these things, W and QC or QH, that should be solvable as well. Okay, what we can
Okay.
only do at what we can really only do here is we can do like some sort of comparison between X and Y. Okay, and if that's the case, let's just go straight here now. If that were the case, we kind of got these already, right?
Yeah.
So if we focus our attention here, and then we can easily see now that the efficiency of Y is just 40% of the efficiency of X, because W over QH is the efficiency of X, right? So that's why I initially answered D as well, because that's the closest thing we can get. But if we knew what Q over
Okay.
H was, then if Q over H was 40% itself, then the answer would be B. All right.
Okay.
All right. So that is the answer to that last bit there. Okay. So at this point, we'll say there is no solution, but the answer is either going to be B or D. All right.
Yeah.
All right. Okay. Let's go now to the question about the entropy. So let's copy this. Oh, hold on. I am not yet streaming. Well, I am streaming. All right, here we go. So here's the problem. So you're given the boiling point, and then you're given the number of microstates, right? So the question is, let's deduce what happens to the entropy of the sample.
This I know.
Okay. Hold on, there we go. The idea here, before we do, I think before that though, I think we've done this problem before.
Not this problem, but I think for A is okay.
Yeah.
I want us to do the second and B.
So just A and A is already okay, yeah. So we'll skip this. Let's go to B. The entropy of a much larger sample during the boiling changes by that much, determining the energy transfer to the liquid. All right, so let me just open up the data booklet again, because we need that for this problem. Thermodynamics. Oh, I ended the stream when you were gone. Well, I'm just gonna say this while I'm getting the data booklet up, yeah? I ended the stream last time, when you were already gone from the lesson, with something which I've seen several times on the internet right now, but I think only physics nerds would kind of get it. All right, I'll get that image later. I'll post it here. Okay, where is thermodynamics? Thermodynamics should be C. No, B4. There we go. All right, so we have two equations for entropy again, right? Let's go to the board. So these are the two equations that involve entropy in the data booklet. One involves a change in the number of microstates over the number of microstates, and one involves the amount of heat transferred. Okay, the first one is actually a definition. That's the definition of the change in entropy. Now, how do we solve this now? We are given the change. That's our delta S. Okay. Okay, so what do we do here? Delta S equals, let's just put the value in now. That's gonna be 12 kilojoules, joules per Kelvin. That's gonna be equal to your heat over the temperature. The temperature here is 70 degrees. We need to convert that to Kelvin. So 273 plus 70 would be 343 Kelvin. So this Kelvin, that Kelvin cancels out. We got our delta Q. So calculator, what do we get? That's gonna be 12 times 343. 116 joules, which is rounded off will be 4.1 times 10 to the 3 joules. Okay, so that's the answer there. All right, is that clear?
Yeah.
Okay, so again, this point, just use the formula straight away. No fancy things needed. Okay. Yeah, just change the temperature to kelvins and we should be good. All right, any questions on this one? On this problem?
No, I just didn't use this formula.
All right. Yeah, the idea there is it's the change that matters, so it doesn't matter how much we actually have to begin with. Okay. All right. I'm now looking at the actual questions you sent me today. Let's see where we can start. Okay, this is going to be interesting. Let's do this first problem here. This next problem here is about the forces on charges. Excuse me.
Yeah.
All right, on the stream, whoever that is, hello. Okay, and welcome to the stream. I hope you understand what we're doing. Yeah, because I gotta tell you. Oh, here's the thing I want to tell you. Before I continue, let's do that. Thermodynamics textbook meme. I'll get a copy of that thing real quick. Is it this one? Yeah, this is gonna work. Okay, before we go to this problem, I'll just put it up here. Okay, this is the thing I ended the stream with. So, just so you know, this is just me saying, don't worry too much about thermodynamics. I'll just go to that bit. That bit highlighted over here. Okay. So, basically these two guys, they were the professor and his student.
Mm-hmm.
Yeah, they ended themselves because they were working on, the joke here is they were working on thermodynamics. Okay.
Oh.
So if they did it, in your case, yeah, don't worry too much about it if you don't get it. Okay, that's what I'm saying. Okay. All right, let's go back here. So here we have to show that in this particular situation, the magnitude of the resultant force, electric field at P is this, 3 mega newtons per coulomb. Okay.
Yeah.
All right.
We don't have to do A. We can do B.
We
I
can
just
skip that. All right.
learned some use.
All right. So that's a setup. So let's go straight to B. Let's turn that off. Copy this image. Okay, let's go straight to B. We now know what the electric field strength here is, right? Does it matter in this case? Let's see. Will it matter? Okay. Explain why Q will perform simple harmonic motion. Oh, okay. Now, this is actually quite easy to explain, all right? We know from here, let's just start it off that that the force is gonna be directed this way. At least the initial force, right? Initially downwards, right?
Yep.
Downwards. Okay. Okay. Then let's just do it here when our particle here, when our point charge is here now, it's gonna go upwards when here, right? F when Q is here, right? Is upwards. Now, okay. Let me see if my tablet's gonna work now. Not quite yet. All right. The idea here now is it says simple harmonic oscillation. This automatically should get into the idea that the force, or rather the acceleration, is proportional to negative x. In other words, what does this mean? In other words, the force, I'll type this in, the force is always opposite the displacement. Force or acceleration, or I'll use the word or here, or acceleration, is always directed opposite the displacement. Okay. Now, let's take a look at the problem here again. Let's see here. If this is your equilibrium position right in the middle, x is up, force is down, right? Similarly here, if you're here, x is downwards and the force is going upwards. So it already gives you that thing, okay, about simple harmonic motion. So the shortest answer here that would give you 2 marks would be okay, hold on. Okay. Okay, let's lock this. And the shortest answer here would be since the force is attractive, the net resultant force, I'll put that in. Okay, resultant force is attractive. The acceleration is always directed towards it's always directed opposite the displacement of Q. SHM, simple harmonic motion, requires that this is the case. That is the acceleration is directly proportional, is oppositely directed. I'll just say it, oppositely directed is directed opposite, I'll just say it like that, directed opposite the displacement. Okay, let's add that part, is proportional to. Okay, that's the answer here. Okay, so also okay, we can establish also from the formula that this is going to be directly proportional. Yeah. Okay. So that's the answer here. If we go back here though, yeah, I think it's fine. I think it's fine. That's already it. It's gonna undergo simple harmonic oscillation because of this. Okay. So part 2, do we need to do part 2? I don't think so.
Yes.
Alright, so let's just go through that. The period. Okay, we know the field strength here. 3 mega coulombs per column squared, right? So let's put that there. The electric field is equal to 3 mega newtons per coulomb. What else do we know? We know that the charge Q is negative 2.0 microcoulombs. Now we know the mass of the object is 0.25 kilograms per and we know that the force is equal to 115 x. Where x is the distance, right?
Yeah.
Okay. Okay, so this also tells me now that it's proportional. Force is proportional to x because from this equation, right? So how do you find the period? Okay, so with this, let's just go into the simple harmonic oscillator formulas. This one I've memorized. I've used these a lot. Okay, so the period, sorry, let's start with this first. The frequency is equal to omega over 2 pi, right? And then the period is equal to 1 over the frequency. So from here, putting these together, the period should be equal to 2 pi divided by omega, the angular frequency, right? Now, that's the first part we need to recognize. The second part is what omega actually is. So remember that we actually have a formula. It's not just the proportionality anymore. We actually have a formula for acceleration related that to x. This is negative omega squared. Okay. So,
Yeah.
okay. So what do we do now? We now can find acceleration by doing force over mass, right? Okay. So what are we gonna do here? We're gonna do force over, okay, F over A, M rather, force over M, that will be equal to, that looks like E, F over M will be equal to 115x divided by, what's our mass? 0.25. That's gonna be our acceleration, but we're more interested in the omega squared, right? And we can put the negative here now because this is just the magnitude from earlier, right? I'll just write here magnitude. Okay, so so once we do this, and let's solve this here, this is gonna be negative omega squared x. So you can easily guess what omega squared is. Omega squared is equal to 115 times divided by 0.25. So we just put this in the calculator what omega is. Okay, so that's gonna be 115 115 divided by 0.25, 460. Let me find the square root of that. So omega is 21.44. Okay.
Yeah.
Now that we have omega, let's put that in here. So the period should be equal to 2 pi divided by 21.44. Okay, so let's put that in the calculator again. Times 2 times pi. That gives us a final answer of 0.29 seconds. Okay, and we've just solved for it.
Okay.
Okay. All right. What part there did you get stuck in before we went through this?
I didn't know which formulas to use to
Okay.
get to it.
All right. So, in these cases where you have a lot of information given, it's always a good idea to go through the basics. So the basics would be like for this. I think the one that would probably be most difficult for you would be this formula.
Yeah.
Okay. Because we have to combine these two facts. Okay. But the rest of it, once you find the acceleration, it should be fine. All right. Any questions there?
Well, no, it's clear.
All right then. Okay, let's see what the next question is. Let's do A, C, D. Okay. Okay, I think let's do question. I think this is together. I don't know which ones are together now. All right. All right, I'll just copy this first. Let's do this part here. And then can you tell me which one this particular question connects to?
Yeah, I tried to send them together. It's the following ones. So,
Okay. So it's the one with that says label the time and velocity graph. Is that correct?
Yeah.
Okay then. All right. So
And the one before it would estimate the loss in mechanical energy.
estimate. Yes, this is the
CV
third one.
and-
All right.
yeah.
Got it. Okay, so I'll just put this here, then the estimate the loss in kinetic energy. Okay.
For this one, I think it's pretty simple, but I didn't understand the graph and why they said that the ball touched the ground at time 1
Okay.
second.
All right. So let's go to the graph first. This graph, right?
Yes.
Okay. This graph is basically just telling you what's happening. Let's go to what's happening first. The ball is falling, then it hits the floor, then it rises up and then falls again, right? Okay.
Yeah.
So think about it this way. When the ball is here, its initial velocity is 0, and then it's falling downwards, so its velocity is negative. So that's that, right? Okay, so this is the part where the ball is falling. Okay.
Yeah.
And then it suddenly changes. The velocity suddenly changes. Why? It hit the floor. It bounces off, right? It bounces off. And then when it bounces off, it goes upwards. So this is what's happening. Boom. It's still on the floor here. And then right here is where it loses contact with the floor. So now, again, it's just falling under gravity. But this time, because its velocity is is positive, that means at this point, the ball is moving upwards. It's moving upwards but slowing down until it reaches the top again, and then it falls back down. Okay?
Wait, sir. After it hits the ground the first time, what happens for this in the slope?
Okay. So, all right. So let's just write that here. So again, this is start, right? This one falling down. Okay. This part is bouncing. Okay. Now let's also label this point. What is this point? This is contact with ground, right?
Yeah.
Contact.
But what is bouncing?
Okay. And then yeah, so this is exact point is when it makes contact, and then this interval here is when it's bouncing, and then here is contact lost. Use lost contact. Okay. So now what's happening here for this section here, this is rising. It's going up. Alright?
Right.
And then here at this particular point here, it again stops. Excuse me, I'm writing. Hold on. Okay. And then here again, it is falling.
Okay. I
Okay?
understand.
Alright, so, hold on. Quick, say hi.
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 Alright, you go.
Ooh, that looks scary.
Okay.
Okay, bye. See you next year. Don't let the science bugs bite.
Alright. Alright, so let's continue. Okay, another somebody from the stream. Hello again. Okay, just listen in. Maybe you'll understand something. I know these kids who are in the stream right now. They're grade 7 students.
Ooh, why they here?
Here to support the channel, I guess.
Oh.
Alright. Anyway, where were we? Alright, so here we go. So that's done. So we've established what the graph means, right? So let's go back now to part 1, B. B part 1. So we label the time and on the time and velocity graph using the letter M, the point where the ball reaches the maximum rebound height. So we've established now what this graph means. Where do we put the answer M? Which point? Maximum height. Maximum rebound height there.
At the after 1.5 the time.
This thing. Okay, that's gonna be M right there. Okay. All right, let's go. Okay, let's go to part 2. State the acceleration at the maximum rebound height. This should be easy now. What is it? What's the acceleration here?
It's 0. No, it's not accelerating anymore. It's just towards the ground. Gravity.
Yeah, it's just gravity now. So, what's the acceleration? The safest answer here is not actually 9.81, but that's fine. Yeah. Meters per second squared. Don't forget the unit, right? This is gonna be a safe answer. But the safer answer here would actually be G. Okay. These would be okay. However, saying 10 meters per second would not be okay because here we are now on the structured question side. On the multiple choice paper, it's still okay to use 10. All right? So here in the structured questions, never answer 10, never use G equals 10. To be on the safe side.
Okay.
Okay. Why did I say safe side? The marking scheme usually is a bit lenient with it. They will accept 10 in certain cases, but you never know when it will not be accepted. Okay. All right. So let's go here to part 3. Draw on these axes a graph to show the variation with time, the height of the ball from the instant it rebounds from the floor. So from the floor, yeah. From the rebounds from the floor until the instant it reaches maximum rebound height. No numbers needed. Okay. So what is it gonna look like?
Constantly decreasing.
Constantly decreasing. So are you sure? It should be increasing. It's from the floor, right? So from the floor, its height is 0. Right?
Increasing at a decreasing rate.
There we go. That's the better answer there. It should be increasing, but a decreasing rate. In other words, a curve like this would work. Okay. Anyway, this is going to be drawn by hand, so this is fine. But if we were really trying to be accurate, this should be a parabolic curve. Okay. So if you would like to make a label like this, that's fine, but you don't have to. Okay. Parabolic curve. Okay. Let's go to the next part. Part C. Estimate the loss in the mechanical energy of the ball as a result of the collision on the floor. It's only 1 mark because it's an estimate. That means you don't have to solve much. But we need to go to the graph. Okay. Okay. It's actually here. You can kind of guess what the kinetic energy is. Okay, are we given the mass of the ball? We are, right?
Yeah.
Okay, so we're given the mass of the ball. We know the kinetic energy at impact. Well, we don't actually know it, but we can guess it from here. We know that we can also find out the kinetic energy at right after, or right at the top of, no, not the top of the bounce, but right after the ball leaves the ground, right? So this is the only part we're interested in. So how do we find the difference there? This is gonna be easy, but the fastest way for me to do this that I can show you is to do this. The change in the energy will be equal to 1/2 times the mass times v f squared minus v I squared. Okay. Sorry,
Yeah.
should be the other way around in this case. Vi actually doesn't matter. Minus vf, right? Now the square, just so we're clear, should be inside the bracket on each of the v's. Okay. So we'll have 1/2 times 0.25. What are our velocities initially? We have, that's gonna be 10 and 5, right? Negative 10 and 5. So if you put that there, 10 squared would be 100. 5 squared is 25. Okay, properly it should be the other way around. 25 minus 100. Okay. So we can now solve this. This is gonna be 1/4, 1/8 of 75. This is gonna be 75 divided by 8. And calculator, being lazy, 75 by, oops, it's my calculator. 75 by 8 gives us 9.4 joules. So 9.4 joules. This is just an estimate, of course, but a good enough estimate for now. Okay.
All right.
I'll just put here VF rather. VF is equal to 5. VI equals negative 10 from the graph. All right. Excuse me. All right, ready to go with continue with D?
Yes.
All right, let's continue now. All right, so let's determine the average force. This one is again pretty easy actually. Since we have force, we're just gonna do F equals ma. Okay.
What do we use for acceleration?
Okay, there. This is where we get. Let's just put that 0.25 here for the mass, right? The acceleration is going to be 5 minus negative 10. Let's see what the time is on the graph. The time that takes is from here, which is 1 second, to here. That is 0.1 seconds, right? So we got from the graph that the time is 0.1 second. Again, this is from the graph. So that's going to be 0.1. So that's going to be 2.5 times 15, right? 2.5 times 15. That's going to be 37.5 newtons. Of course, 2 sig figs, that will be 38. Okay. Alright. Suggest why the momentum of the ball was not conserved during the collision with the floor. Conservation is not conserved only means one thing. Energy was lost somewhere. It got out of the system. And our system here is the ball on the floor, right? So that's always what you think. Where did the energy go? And then that's gonna be an answer there, okay? Momentum, that means some energy was transformed to something, right? Was transformed to, let's say, something. Let's put heat. Okay. Leaving less kinetic energy available to be. Leaving less kinetic energy, less velocity, less momentum. So smaller VF. So meaning smaller. So meaning different momentum. Okay. So momentum changed.
Okay.
All right, that's it. Okay. There you can also answer this in terms of forces, but you have to identify what the forces were that made it change the momentum. Okay. So in this case, if we use, it's gonna be easier to do energy when it comes to this though. So just stick to this explanation.
Okay.
Okay. Right. That was pretty fast. Where's the next one here? Alright, so that's done. Okay, hold on. There's still a part. We already did that. Never mind. That's done. That's done. Okay, the last two are together, right?
Yes.
Alright, let's do the last problem here then. Alright. Okay. Is that a train?
It's a tram. It's really loud.
The tram, yeah.
Yeah.
Alright. Also, you live near the tracks, I see.
Yeah.
Okay. Let's just copy this last image here. Okay. Okay, and then let's answer. Okay, put this here. Okay, so let's go now. So you have this standing sound wave, and again, this standing wave is actually a longitudinal wave. It's just easier to represent it with a transverse form. Okay, right.
Yeah.
So, so establish in a tube that's closed at one end, open at the other. The period of this wave is t. Okay, the diagram represents the standing wave at t equals 0 and t equals 1/8. T over 8. Okay, wavelength is 1.2. Positive displacements means place it to the right. Okay, and what just happened? Just put it back. There we go. Okay, so calculate the length of the tube. Okay, this is the length of the tube is actually quite easy. Remember that the wavelength is given to you, right? How many wavelengths is this though? In terms of the actual wavelength, how many wavelengths is that? You can think of that as 1/4 of wavelength, and that's 3/4 of a wavelength, right? And we'll establish that equation right there. Okay. So from here, what do we put in? The length. Let's just use that equation now. This should be 3/4. My mistake there. 3/4 times the wavelength, which is given 1.2 meters. So that's gonna give us that gives us 0.3, and therefore the length is 0.9 meters. Okay.
Yeah.
All right, so let's go to the second part. A particle in the tube has its equilibrium position at the open end. Equilibrium is open end. Then explain the direction of the velocity at this. Okay, so here, remember it's given here that positive displacements means displacements to the right. Okay, so now remember this is in a, let's mark the equilibrium, and let's say that's E for equilibrium, right? But its current position is actually to the left of it. So this translates to that. Okay, so this is the position at t equals 0, actual, right? Actual. Okay, and then that means it's gonna start moving that way at this point, because at t to the 8, at t equals t over 8, it's a bit closer, right? So that means it's going that way. This means that this particle here is gonna move that way to the right. Okay,
Wait, sorry.
Go ahead.
Why is it moved? Why is it moved to the left?
okay, all right, let's do that again. Okay, okay, let's do that again so it's easier to see. So again, we mark the equilibrium right here, right? Okay,
Yeah.
so, and I'm gonna use, let's change it to red. That's the equilibrium position. So what does this mean? This means that the position that at time equals 0, the particle is to the left, because of the fact that it says here positive displacements mean displacements to the right. Okay, particle is to the left of, oops, what just happened? Left of E. Okay, that's what this means. Okay,
But that is in the negative part.
yeah, so of course, because it's negative, that's why it's to the left, because it says that positive means to the right. Okay, because, and now that it's to the left, where is to the left of E? So that means we can mark at some sort of position here. This is t equals 0. That's the position of the particle. Okay,
Okay.
now
Yeah.
this also means this is going to be here, somewhere here. This is t, I'll use a different color. Let's use green here. Okay, so for this position, this is t equals period over 8. Okay,
Yeah.
all right. All right, so explain the velocity now. So now that we've established what these graphs mean, how is it moving? How is the particle actually moving? From t equals 0 to t equals, it's moving that way, to the right. Okay, got that?
Yeah.
Okay, so how would we write that now? Let's just put this here. So the particle is moving, sorry, the velocity, right? The velocity of the particle is directed to the right as it starts at the maximum position on the left. Okay, to the on the left, and at t equals t over 8, it has moved to a closer position, to a position closer to the equilibrium position. Okay, a position closer to equilibrium. That's it.
Okay.
Okay, so that's the more refined version of it. Hey.
Yeah. I wanted to ask also, Last lesson we talked about the electrons and them being seen as waves.
Yep.
And there was an experiment that they did when the electrons made like a circular pattern.
Oh, yeah. Yeah.
I forgot what it's called, but could we go over it and could you explain how it works?
Okay. All right. We do have time. So, do you still want to do 3 or do we go straight to that?
Yes, after 3.
All right, let's do 3 then. So draw the diagram of the standing wave at t equals 1/4, period over 4. So remember, at what you can think about this is the period can be divided into 4 main regions, no matter what the wave is. So let's do this here on a generic thing first. So remember, let's establish this. This is gonna be t, right? So what's this? This is t over 2. Okay, and therefore this is t over 4, and this point here is 3t over 4. Okay, or you can think of it that as that's 1/4 of a wave, that's 1/4 of a wave, that's another 1/4, it's another 1/4 of the wave, right?
Yeah.
Okay, so let's go back to our initial position here. Our initial position is here. So let's use blue. So here's our initial position. It's at the other way, sorry. Should be here, right? The initial position here. Then you move from here to here. You take 1/4 of the period. Where do you end up?
T.
That's a time, but in terms of position, that's equilibrium, right? So
Yeah.
this is gonna be displacement, and therefore this is displacement equals displacement is equal to equilibrium, right? For this particular line. So again, at this is equilibrium position. So the idea now is the same thing. If this is t, you go 1/4 of the period. That means you're gonna go here to equilibrium. Okay. So the diagram, since it's at equilibrium, and for a standing wave, everything is in equilibrium when one is in equilibrium. Sorry, not one, but when the antinode is in equilibrium, everything's in equilibrium, right? So the correct waveform here will be this. So in the exam, if you have a ruler, use a ruler there. Otherwise, this is good. Okay?
Okay.
All right. So let's go back to your question. Let me try to find an image of that. Diffraction pattern, a circle. Let's see. Let's look for an image. All right. I think you're saying something similar to this. Okay. Thank you, Hyperphysics, for the image from the internet. I'm crediting you there first. All right. Okay. Are you talking about a pattern that looks something like this? Oh, it's taking its time. This particular pattern right here.
Yeah.
Okay.
But there was the whole machine
Mhm.
before that.
All right. But I'm gonna do this in terms of the laser because remember when this was done with electrons, it's the wave properties of the electrons that are being used already. Okay.
Yeah.
So to make it a bit easier to visualize, we're not gonna deal with electrons themselves. I'm gonna look for a good image here that would say how it would look. All right. Excuse me. Now, again, I think I'll just borrow up that. Okay. Let's look for a good one. Okay, I think this is good. Copy image. All right. ASC Physics and Astronomy. Thank you for the image. All right. So what's gonna happen because of what we've already learned before basically is when you have slits, single or double slits, or no matter how many slits you have, you would get some sort of interference pattern that looks like the one here on the right, like this thing, right?
Yeah.
Okay. Now the idea here is once the hole is no longer a slit but a circular dot, it changes the way it looks on the screen, But it doesn't change the way it looks like if you look at it on 2 dimensions like this. It still will have the central maximum, then a minimum, then a maximum, then a minimum, maximum, and so on. Okay? So, alright, so in this case, what's gonna happen is, again, once you have your circular pattern, this simply means you have a circular hole. If you have a series of the fringes rather than a series of circles like this, so this is 4 circles, right? Circular diffraction pattern. Okay?
That's only because of the surface of the
This is big.
material.
Yeah, this is more about the. It's gonna be hard to explain it without the actual thing, isn't it? But okay. The idea here is when you have you done this sort of experiment before?
We haven't done it, we just saw the image.
Oh, you know what? It's such a shame. It's actually easy to set this up in a school lab.
Really?
Yeah. I just set it up with a laser pointer and a piece of a hair.
Oh.
Yeah, but anyway, okay, the idea here is we get a diffraction pattern with the hole, right? But the same diffraction pattern can be observed if instead of a hole, or why did I stop sharing? Hold on. All right, let's go back. So the same diffraction pattern can be established is instead of having a hole, you have a circular object here, or a spherical object, anything with a cross section of a circle. Okay, so once the light goes in, and we're still talking about light. Okay, once the light goes in and then it goes around that, and then you put the diffraction pattern on the screen, you'll get the exact same thing. You still have your central maximum, you're still gonna get that same generic pattern like that. Of course, same thing here, right? Okay, so it doesn't matter whether you have a hole with a solid barrier on either side, or you have a solid object with empty space on either side. You'll get the same results. Okay?
Okay.
Alright, now, what happens with the electrons? When you change the light to electrons, because electrons tend to have really small wavelengths compared to light, right? So what happens here? If the wavelength is comparable to the, I'll write that here. If the wavelength is comparable to the barrier size. Again, the barrier here could be the hole or the object, yeah? If the wavelength is comparable to the barrier size, a clear diffraction pattern will be observed. This is the key idea here.
Sorry, but what does it mean, comparable?
Okay, hold on, is observed. What I mean here by comparable is they're approximately equal. They're of the same order of magnitude would be the better way. Okay, observable.
Okay.
Okay, comparable, I'll write it here, same order of magnitude. Okay. Okay, so again, if the wavelength is the same order of magnitude to the barrier size, a clear diffraction pattern is observable. If the orders of magnitudes are way off, you won't see a clear diffraction pattern. Okay?
Okay.
All right. So what happened? I'll just describe the experiment now. So what happened? So when electrons were fired into molecules and atoms, we got diffraction patterns. That means the wavelength of a molecule, the wavelength of an electron is comparable to the diameter of an atom.
And the distance between them.
Yes, and also the distance between the atoms, correct. So no matter how you look at it, whether you're looking at single atoms or you're looking at a collection of atoms. Okay? All right. So once you have the diffraction pattern, and of course that's what physicists do once they find there's a relationship, they look for possible patterns, and then they just kept experimenting with different substances to do this. And all the predictions got confirmed. So that's one confirmation that electrons do have wave properties.
Okay.
Okay. All right. Okay, is there anything else you'd like to ask here now? I think that's it for today.
Yeah, I understood everything. Thank you.
All right, great. So we'll just continue again on the next lesson. I see you need to reschedule some lessons soon, so just go ahead and find a free time for yourself, okay?
Okay.
All right.
Perfect.
Perfect. So let's stop the sharing there. And we'll end here today. I'll see you again next time, Geeta. You have a good day.
Okay. Have a good day.
All right.
Bye bye.
Bye-bye now. All right, that's the end of that lesson. And let's go back to the stream. I wonder if you guys are still there. Are you still there? Just say hi if you all are still there. Yeah, I appreciate the fact that you came up and said hi. Either way, whether you're here or not, yeah, I appreciate that. So thank you for coming. All right. I guess we'll end the stream there. I hope you did learn a few things. Before we end though, so again, I'd like to remind you to like, share, and subscribe to the channel. We are on YouTube, Facebook, TikTok, Instagram, and when we stream, we're live on Twitch as well. So with that, I bid you all, wherever you a good morning, good day, good afternoon, good evening, good night, wherever you are in the world. Stay freaky, everyone. Bye bye now.